continue with our discussion on performance evaluation of processors. In the last lecture, we saw that there could be different angles or different perspectives when you look at the performance issue, and therefore the definitions may change. We try to follow the definition which would be true for a individual user's perspective, and from that point of view, we try to define performance in a quantitative manner, essentially trying to say that it is execution time of a given program over an architecture, over a machine, which matters. So we'll probe further into this, look at more examples, and try to see how this is done professionally, so that a large community of architects and users could share same ideas. So essentially the formula or the definition we came up for performance tried to interlink three aspects: the number of instructions which you require to execute a program, the number of clock cycles which are required to execute a program, and the total time which is spent in executing a program. So these are three ways or three aspects which are of concern to you. The one at the bottom is the number of seconds. Okay. How much time, how many seconds or minutes or hours are taken to run a program. This could also be expressed in terms of number of clock cycles, because everything which is done in a computer is in terms of clocks, and also one could say at slightly higher level that everything is done in terms of instructions. So the time taken could be measured in these three units, where this is more abstract, less abstract, and least abstract. Okay, so this is a real measure, and there are quantities which we defined which link these. So for example, the relationship between instruction and cycles could be expressed as cycles per instructions. Okay, number of cycles you require to do an instruction. You can talk of individual instruction, you can talk of a collection of instructions in terms of its average. So when you're talking of entire program, what would matter is average CPI or average cycles per instruction for that particular program. Now remember that this average could be different from program to program. Same thing actually said in a inverse manner is often called IPC, or instructions per cycle. So the notion here is different, that as if you are trying to do multiple instructions in a cycle, and there are machines, there are processors which actually are at that level of performance where they do multiple instructions per cycle, and there it becomes perhaps more important to talk of instructions per cycle. But for this particular course, when we are talking of basic architecture, we will essentially confine ourselves to CPI. One could say that the two are reciprocal of each other, but it is the perspective which is different. Then what relates cycles to the absolute time is the clock period, or conversely clock frequency. So that's something very straightforward. Finally, the relationship between instructions and the absolute time. Okay, you could talk of the total time each instruction takes, okay, seconds per instruction, or you can also talk of instructions per second. So when you're talking of time, second per instruction, there is another thing which we actually talked last time, was seconds per program. Okay, for entire program how many seconds are required, or for one instruction how many seconds are required. One could ask both questions. So when you're talking of time per instruction, it is actually talking of instruction rate, and may not really capture the entire picture of how long a program takes. Okay, a program may execute at a fast rate, okay, but the total instruction may be large, so it is the overall time which matters. But still, often one talks about the rate at which instructions are done. So instructions per second, and since this to make a more convenient unit, we talk of million instructions per unit, or MIPS. Okay, so this is the average rate at which instructions get executed, right? Reciprocal of this would be the number of microseconds you are spending per instruction. So one could talk of MIPS as an average. People have also talked of peak MIPS, which is because the if you look at the instantaneous rate at which instructions are done, it could vary. There are slow instructions, there are fast instructions. So peak MIPS would refer to if you were doing only the fastest instructions, what is the rate at which you will do it. Okay, so in nutshell, what we have said is that performance is determined by execution time, particularly an individual programmer or individual user's perspective. At different stages, people have talked of other ways of looking at it, and the question is, do any of the other variables truly represent performance? And some of these possibilities are number of cycles to execute the program, number of instructions in the program, number of cycles per second, average number of cycles per instruction, average number of instructions per second. So I've talked of many of these things, but ultimately it is this which is important, the execution time. Here, when I'm talking of number of instructions in program, this is a factor which is often looked upon in two different ways. One could be the length of the program. As you see statically, a program has so many instructions. Okay, how many megabytes or kilobytes it occupies. Okay, that's linked to the number of instructions it has. But when you are talking of performance, you're talking of dynamic number of instructions. That number of instructions executed would be the right term. So if the program has some loops, of course some instructions get repeatedly. So from performance point of view, you have to count those many times. Or if there are conditionals, something gets skipped, something gets executed, you have to see what gets executed. So to do some computation for a given data, program executes certain number of instructions, and that's what one is often talking of. So a common pitfall is thinking of other possible indicators, okay, which are not true indicators of performance. They may be related, but they are not true indicators. Okay, now let's look at a few examples. We looked at last example, one example in the last lecture towards the end. We'll see a few more today. So suppose we are talking of two implementations of the same instruction set architecture, or ISA. Let's call these A and B. So instructions are same, okay, but there are two different ways of implementing them in hardware, right? So now for a given program, suppose A implementation has a clock cycle time of 10 nanoseconds and B has 20 nanoseconds. The CPI, the rate at which instructions get executed, or number of cycles per instruction on average, is 2.0 in case of A and 1.2 in case of B. Okay, so the question is that for this particular program, which machine or which implementation is faster? So we can apply the formula which says that you take the number of instructions executed, multiply it by CPI and multiply it by clock cycle time. Okay, so one question you need to answer is that if these two machines, as the case is now, which have same ISA, which of the quantities remain equal? Number of instructions, because it is the same program expressed in the same instruction set which we are talking of. So it is the number of instructions which will remain same. Other things could vary. Clock rate is given to be varying, CPI is given to be varying, MIPS or the rate at which instructions are done will vary, and so would be the execution time. Okay, it's only the instruction, the number of instructions executed, that will remain unchanged. So now we are not given the number of instructions in this case. All we know is the two are same. So our objective is to find relative performance, or just find which is faster, which is slower. So that can be done, and therefore we can knock off that common factor, which is number of instructions. So essentially you take product of these figures, okay, 10 nanoseconds and 2.0, which basically says it is 20 nanoseconds is the average time you're spending per instruction, and it is the same instruction where 24 nanoseconds is the time you spend per instruction in the second case, and clearly A is faster. Okay, another example. Here situation would be such that the number of instructions would vary. Okay, so suppose put yourself in the shoes of a compiler designer who has to decide between two alternative sequences of code to translate a given high level language computation. Okay, there is some statement in high level language, it can be translated in two alternative ways. Okay, and one has to make a choice between these two. So the architecture which is available to him, the instruction set architecture, offers three classes of instructions, A, B and C, and they differ in terms of course their functionality, but in terms of cycles, the number of cycles spent is 1, 2 and 3 in the three cases. Okay, class A instructions take 1 cycle, class B 2 cycle, and class C 3 cycles each. So the options which the compiler designer is debating are these two code sequences. First sequence uses two instructions of type A, one instruction of type B and two instructions of type C. Okay, for same computation. So this is one possible way one could translate same computation. Second way is you have 4 of A, 1 of B and 1 of C. Alright. So now how do you evaluate this choice? You can find out the time which will take for both these cases, and you can see that in first case, okay, the same sequence, this sequence will require a total of 2 plus 2 plus 6, so that is 10 cycle, and in the second case it will require 4, 1 and 1, so which means 4 plus 2, 8 and 3, 11. Okay, I'm sorry, what did I do? 4 plus 2, 6 and 3, 9, yeah, 9. So second is faster. Alright, although the total number of instructions in second one is longer. So if you were just to compare number of instructions, first sequence is of 5 instructions, second is of 6. Alright, if you don't go into timing, you might say first sequence is shorter, and one may be tempted to do that, but only when you look into the cycle information you realize that essentially what second sequence does is it trades off one slow instruction for two fast instructions and still makes sense. Okay, so one could quantify the difference. How much is sequence 2 faster? So it is 9 versus 10. Alright, and you can also find CPI for each. So what is the average CPI in the two cases? Can you do it quickly? 2. So it will be basically you add these, you take average of these with these as weightage. So it is 2 plus 2 plus 6. Okay, so basically we have already counted the number of cycles, we can divide by number of instructions. So 10 cycles for 5 instructions, which means 2. So CPI on the average is 2, and here you have 9 cycles divided by 6, so you have 1.5. Okay, yet another example. So we have two compilers which are being tested for a machine. Again there is kind of similarity. Once again the compiler is the one which is varying. So the clock frequency is 100 megahertz, and there are three classes of instruction. Similar situation, 1, 2 and 3. Three classes are A, B and C. So compiler 1 produces for a given program. Now we are looking at entire program. Situation is similar, but instead of some piece of code we look at one whole program. So compiler 1 produces 5 million instructions of type A, 1 million instructions of type B, 1 million of type C, and second compiler produces 10 million of type A, 1 million of type B, and 1 million of type C. So it is just producing more instruction in of type A, and others are same. So now which compiler gives you higher MIPS? Okay, the first, okay, let us say all right, you can add these add the cycles of these instructions, right? And you know that the cycle time or the rate at which cycles are running is 100 megahertz. So total of cycles required for these instructions will be 5 million plus 2 million, that is 7, and 3 million, that is another 3. So total 10 million cycles are required, and each cycle takes 0.1 nanoseconds. All right. Let me see. No, we are trying to talk of instructions per second. So 10 nanoseconds multiplied by 10 million cycles is how much? Let's see. It's 100. So 1 by 1000. So 1 by 10 seconds is what you would require. Okay. So you have, am I right? Yeah. So you have executed 7 million instructions in 1 by 10 seconds. Is it right? 1 by 10. Just check my calculations.
Yes.
Okay. So 7 million instructions in 1 by 10 seconds. So what is the instruction rate? It's 70 MIPS. Okay, 70 million instructions per second. Right? Let's do it for the second case. So the number of cycles here is 10 million for this, 2 million for this, and 3 million for this. So basically 15 million, right? And the total time spent would be 15. Sorry. It should be 1.5 times that. So 0.15 seconds as opposed to 0.1 seconds. Okay. In case 1, we spent 0.1 seconds. Now we are spending 0.15 seconds. And the number of instruction being done is 12 million. Okay. So what is the MIPS we are getting? 80 MIPS. So the answers are 70 MIPS in first case and 80 MIPS in the second case. So if you were to take MIPS as the comparison criteria, it might appear that in the second case you take the second program generated by the second compiler, it's giving you faster MIPS, more MIPS, right? But it is obvious that the total time spent here is more, and therefore compiler 2 is producing a poorer code. Okay, so execution time is lower in first case. Okay, so in that sense it is better, whereas MIPS is higher in second case. So apparently the second may look better, but one has to be careful here. So is it clear? Okay, again in this example we have two implementations of same instruction set architecture, right? So again instruction set is same, these two are being called M1 and M2. They are different in clock, okay, 50 megahertz in one case, 75 megahertz in the second case. The CPI is also different, 2.8 here, 3.2 here. Okay, so apparently what's happening here is that you have a longer clock cycle, but more work is getting done in each cycle, and here you have shorter cycles, so less work is getting done in each cycle. So you take more cycles here, less cycles here. Now how do you find the composite effect of these two? How do you compare? So the ratio of execution times of M1 and M2 would be the instruction count multiplied by CPI divided by clock rate of M1, and instruction count for M2, CPI of M2, and clock rate of M2. Now it is the instruction count which is common, being the same instruction set architecture as we have seen earlier. So we can look at the remaining factors, 2.8 by 50 and 3.2 by 75, which comes out to be 1.31. Okay, so it means that M1 takes longer as compared to M2. And the factor is that it is taking 31% more, 31% longer than what M2 takes. Now question could be asked in different ways also. Okay, so if you had a redesign possibility for M1 and you were able to increase the clock rate, keeping everything else same, keeping let's say CPI same, what clock rate for M1 would give same execution time? Okay, so here what you can do is you can keep this factor as unknown and put this as 1, and that will give you the clock rate you require, right? Okay, so I don't go through that calculation, you can check it out. Okay, so now we have seen these examples where we try to see what happens if you change the design, what happens if you change the compiler. Similarly, you can examine the combined effect of both. So in tutorials probably we'll take exercises which will try to look at more complex situations. Okay, but now we are faced with the question of which program you should use to check out the performance, right? If you are a very focused user, you have a single program which you want to run over and over again, then there is no problem. You can just see how long system works for that particular situation. Or if you have not just one but a small set of programs, or your workload typically is some 5-6 program you do over and over again, you also may have an idea of how often you use program 1, how often you use program 2, and so on. You could test for all of these and get take some kind of average. Okay, depending upon your area of application, for example, you do maybe compilations, editing, run some scientific application. So depending upon your area of application or your typical workload, you can always work out. But the question is that can you do something in a more general sense? Okay, so this is very personalized way of evaluating performance, but are there general attempts? Okay, in general, can you say A is better than B, or so on? So for that one has what is called benchmarks. Okay, benchmarks are basically programs used for testing the performance. It could be a single program or a set of programs which collectively are used for testing the performance. But one has to bear in mind that benchmark has to be or set of benchmarks have to be appropriate for a user or a set of users. All right. If a user runs commercial applications, then benchmark should be of that type. If user runs a heavy scientific application, then benchmark should reflect that kind of application. And benchmark should be such that they test a given machine extensively. It should not be that they test some particular feature and a machine which is better in that feature but not better on the whole would give a false improvement of false sense of related performance. So the benchmark should not be overly dependent upon a few set of features, so that a machine vendor can also misrepresent the level of performance. So one can think of benchmarks of a varied complexity. It could be very small, simple benchmarks, and they could be very complex, and accordingly their usefulness would vary. So who defines these benchmarks? Okay, benchmarks can be defined by users or the vendors, or maybe mutually agreed upon. Small benchmarks are easy to write, okay, and they are nice for discussing the performance by, let's say, designers and architects. You can closely see what is happening, how a benchmark is performing, where it is not performing, and you can analyze it very nicely. They can be easily standardized, but they can be abused. So, for example, there have been cases of small benchmarks and cases where computer vendors would generate very highly optimized code for that particular benchmark. So you could in fact have a switch in your compiler that if the code is this, just if the source is this, put this as the code, and it could give again a false sense of high performance. So a consortium was developed in middle of 90s, which is called SPEC, and it stands for System Performance Evaluation Cooperative. So there are a number of industries who have joined hands to standardize this process of defining benchmarks, declaring performance, summarizing and tabulating the performance, and bringing a common platform to this issue of performance evaluation. So the attempt here is to take real programs. Do not write small artificial or synthetic programs, but take real programs which users use and standardize them, take some standard implementations, define some test inputs and so on, and make them available on a common platform. So one could still abuse these, because even in large programs what may happen is that a lot of time gets spent on small pieces of code. So if you could really attack those and make your machine work faster for those, things can go wrong. But since you're talking of not just one benchmark but a collection of benchmarks, number of programs, and it may be somewhat harder to pick out the critical code of each of the programs and make your machine work fast for all of them. Okay, so one could abuse, but chances of such abuse are much less. And these benchmarks are valuable indicators of performance of hardware plus software, the total environment in which you use. That means you are talking of a machine, a hardware, and a compiler which generates the code, because these benchmarks are not defined in assembly language of a particular machine. They are defined in standard high level languages, and therefore role of a compiler is important. So what one is evaluating is not just the machine but compiler plus the machine combination. So this is a typical result of carrying out a set of benchmark tests for a given machine. Alright. So here you are showing comparison of benchmark figures for two different compilers and the same machine. So this lighter color is for one compiler, and this orange one is for second compiler, which is an enhanced version of the first one, improved version, does certain optimization. And the text is actually very small here, so you may not be able to read. What we are showing on the vertical axis is the performance rating. Okay, so this is a number where higher number means higher performance. Okay, and this number is obtained by running the program, finding its time, and taking reciprocal with the certain scaling factor. Okay, so higher the number means higher is the performance, or lower is the execution time. And you would see a pair of bars. Each pair corresponds to one particular benchmark. So this one is, for example, GCC, which is a C compiler. So it is the time compiler takes to compile a program, which we are actually measuring here. So GCC compiler was compiled by this compiler and that compiler, and the two times are different. There's a marginal improvement in the rating. You don't see much difference here. This is Espresso, which is some circuit optimization program. Spice is a simulation program, and so on. So this is another. This is Lisp interpreter. So here you would see what has happened, that between light orange and dark orange there is a dramatic difference. So essentially what this compiler did was some clever trick that this matrix oriented program, it could optimize some very crucial part of that program, some loops, and give a dramatic performance improvement. But if you look at in totality, there is an improvement, but not so dramatic. If you had looked at this in isolation, you would have startling results. So what are these benchmarks? Beginning with sometime around 95, a set of programs get defined as a set of benchmarks. Okay, there are two sets actually. Those which are involved in integer computation, so spec int, and spec fp, which is floating point. Okay, so because user who work with floating point, heavy numerical computation, they have different set of typical programs. Those who work in symbolic computation or in non-numeric computation, the set of benchmarks may be different. So in the integer case, you have things like compiler, simulator, Lisp interpreter, and so on. So here is a set of benchmarks and names, so you will get some idea. So Geo is some artificial intelligence program, plays the game of Geo. M88K Sim is a Motorola 88K chip simulator, so it simulates a processor. GCC is a GNU-C compiler. Compress is a program for compression and decompression of files. LI is Lisp interpreter. IJPEG is graphics compression decompression. Perl is a benchmark which is written in language Perl. It manipulates strings and prime numbers. Vortex is a database program. Tomcat V is a mesh generation program. Swim is the shallow water model. I'm sorry, these are not just these are actually a mixture of integer and floating point. I can see both here. Then there are benchmarks from quantum physics, astrophysics, 3D equation solver, partial differential equations, something which simulates turbulence in a cube, solves problem regarding temperature, wind velocity, and pollutant distribution. This is from quantum chemistry, this is from plasma physics, and so on. So these benchmarks have been revised from time to time, because as time changes, the applications change, the machines change, the amount of memory which is available in the machines which were prevalent in 95 is not same as what is available today. Okay, so you need different programs, different set of programs to evaluate and benchmark contemporary machines, and therefore periodically these keep getting revised, and it is always meaningful to work with the current set of benchmarks. So using these benchmarks, you can answer a variety of questions. For example, you may take same machine and look at its two different versions with different clock rate, okay, and ask a question whether doubling the clock rate doubles the performance or not. So here you ran some program of spec-int set over Pentium and Pentium Pro. Okay, so this refers to Pentium, this refers to Pentium Pro. For each case, you have done it with different machines. So for Pentium, it is 100 megahertz, 150 megahertz, and 200 megahertz. And how much is the performance varying? Here it's something like 3, little over 3, and here it is little over 5. So the clock has been doubled from 100 megahertz to 200 megahertz. But as you can see, this number has not doubled. It is less than double. So what could be the reason? In our formula, we had clock frequency as a proportional factor. What happened to that? Pardon? Okay, suppose cycle per instruction is also same. Yeah, what has happened here is that our formula does not take into account the memory speed. We are assuming that there are no additional cycles for memory. So either you have to count them separately or actually adjust them in CPI itself. So you could have effective CPI which would try to take into account extra time which may get spent if memory is slow. So when we are doubling the processor frequency, we have not said that have we doubled the memory speed also or not. So we will look at memory effect later. This is just to remind you that we are looking at still in a very small domain, just looking at processor. But when you account for other things, memory, I/O peripherals, and so on, things become a little more complex. But these benchmarks are run on physical systems. Okay, so memory is there, I/O is there, everything is there, and you have run a program from end to end, from input to its output. So in this case, in this diagram, the question which is being asked is, can a machine with slower clock have a better performance? Okay, again simple question. So same two machines, Pentium and Pentium Pro, same 3 points. The benchmark we have taken are spec FP, that means for floating point performance. So here you could notice that Pentium Pro with 150 megahertz is outperforming Pentium with 200 megahertz. Alright, so although they have same set of instructions, Pentium Pro has a few extra, of course, but the way the instructions are implemented is different, and therefore with the lower clock itself it can outperform. Okay, so we are actually concerned about speeding up execution of program eventually by various means, by improving the architecture, improving instruction set, improving the hardware implementation, improving compiler, the way code is generated. But we must keep in mind very simple but important law called Amdahl's law. Okay, so first let's define what is the speed up. Okay, so you have some old execution time and you have hopefully reduced new execution time. You take the ratio and that factor gives you speed up. So it's simple. Or alternatively, you could take the ratio of performance figures which are reciprocal of execution time. So performance of new or performance of old. Now what happens is that quite often you may speed up only part of the program execution. So let us say this big rectangle represents the entire program or the time spent by an entire program, and your attention was focused on this shaded area. So it is this part you're focused on, you have designed your architecture or compiler so that this gets speeded up. Okay, so or there is a technique which you have in mind which affects only this part, does not affect rest of the part. So suppose this time shrinks to this by certain amount, where the remaining part remains unchanged. So what is its effect on the whole? Let us say we try to figure out the fraction which is enhanced and fraction which is not enhanced. So fraction subscript enhanced of the task is speeded up by a factor called speed up subscript enhanced. Okay, so this is a fraction. Let's say you might say that I am taking 3/4 of the program or 75% of the program and speeding it up by a factor of 2. So these are the figures I am talking of. This is a fraction of the program you are speeding up, and that's a factor by which you are speeding it up. So the new execution time can be now related to old execution time by this factor. So what you're saying is that 1 minus this fraction remains unchanged. Okay, and the fraction which you enhanced is reduced by this factor. Okay, so if you had, for example, 75% of the program speeded up by a factor of 2, so this 0.25 remains unchanged, and 0.75 divided by 2 is the contribution of that speeded up part. So the speed up would be the ratio of these two, execution time old and execution time new, and what you get is 1 upon this. So now basically this is how the law is captured, and this law says that you have to keep in mind the part which is being speeded up, and often you are not speeding up the whole thing. So the effect of this in the overall speed up may get limited by how big this fraction is. So if you are only taking half of the program and speeding it up by a large factor, still the total speed up cannot be more than 2. Okay, you get that? Suppose your attention is only on half of the program, and you might infinitely speed it up, but the overall time cannot be more than 2. Overall speed up cannot be more than 2 because other half remains as it is. So execution time after improvement is time which is unaffected, that we take as it is, and time which is affected is divided by the improvement factor. So now quantifying that with an example, suppose the program runs in 100 seconds on a machine with the multiplication instruction responsible for 80% of the execution time. So 80% of the time you are only multiplying, and remaining 20% you may be adding, subtracting, loading data from memory, taking decisions, branching, and so on. So it's a for whatever reason it's a multiply or multiplication dominant program. How much do we have to improve the speed of multiplication if you want to have the program run 4 times faster? Okay, so from 100 seconds we want to reduce it to 25 seconds. So what is the speed of factor required for multiplication alone?
16 times.
Pardon?
16 times.
16 times. Okay, so you can see that there is a huge improvement you need just to get 4 time improvement. So your effort is to make it 16 times, but the net result you get is only 4 time improvement. Okay, so of course one principle which underlines all this is that you always have to find out which is the common part, and that has to be made fast. So you have to pick up, well, 80% is a good enough fraction here, right? Had this been even lower, as I mentioned earlier, 50%, or if it is small fraction, then your achievement is much less. So you have to take something which is common and try to improve it as much as you can. So another example, suppose we want to take a machine and enhance its floating point capability. Okay, suppose the floating point instruction is speeded up 5 times, execution time of some benchmark before the floating point enhancement is 10 seconds, what will be the speed up if half of the 10 seconds is spent executing floating point instructions? So now we are talking of a smaller fraction, only half the instructions are floating point, and we make them run 5 times faster. So basically you could say that this 10 seconds was divided into 5 and 5. Okay, 5 seconds are remaining unchanged. Remaining 5 seconds are speeded up 5 times. So that gives you 1 second. So total time now is 6 seconds. So from 10 you have gone to 6, and therefore speed up is 10 by 6 or something like 1.67. That's the factor by which you have speeded up. Okay, again a question. Suppose we are looking for a benchmark to show off the new floating point unit described above in the previous case, and we want the overall benchmark to show a speed up of 3. Okay, one benchmark we are considering runs for 100 seconds with the old floating point hardware. How much of the execution time would floating point instructions have to account for in this program in order to yield the desired speed up on this benchmark? Okay, so the previous program where you had only 50% of instructions, 50% of the time spent on floating point, will never show you a speed up of even 2. Okay, it will always be less than 2. In the previous case we got 1.67. Okay, but suppose you wanted to project your floating point improvement. Okay, what kind of benchmark you will have to choose, right? You want to choose a benchmark, you want to synthesize, you want to take a benchmark which will show that with this floating point improvement the whole thing runs 3 times faster. Okay, so now we are asking the question a little differently. So can you tell me what fraction of the original program should be floating point computation?
83%.
Pardon?
83%.
83%. Is that, does everyone tell you that? Okay, you can work it out if you can't quickly work it now. Okay, here now let's look at improvement which takes place with technology. Okay, improvement with time. Assume a processor currently requires 10 seconds to run a program, and processor performance improved by 50% every year. Okay, let us say in simple terms, you're getting X megahertz today. Next year you'll get 1.5 times X megahertz. Next time it will be 1.5 into 1.5 times X, and so on. So every year you are seeing that the performance is going up by 50%. So by what factor performance improves in 5 years? But it's very straightforward. 1 plus 0.5 raised to power 5, or you get a factor of 7.59. And execution time after 5 years would reduce by the same factor. Okay, so if it is 10 seconds now, it will become 10 by 7.59 or 1.32 seconds. So it is nice, but can you spot what assumptions we have made, what simplifying assumption we have made in this calculation? Sorry?
The clock rate is being changed, nothing else is being affected.
Yeah, that's one assumption. And again, let me again remind you that we have not said anything about the memory. Is memory improving by same factor or not? Okay, so here we have effectively assumed memory also improves by same factor. If it does not, then things will be different. I have mentioned already about a possible performance indicator which people have used is MIPS. Another one which has been used in past is M-flops or megaflops. So particularly for floating point operations, people have talked of M-flop, which stands for million floating point operations per second. All right. So it's a metric again similar to MIPS, which is talking of million instructions per second. But here the focus is on floating point. So which is somewhat relevant for people who do predominantly floating point computation. But once again, there are other things which are there in the program. It's not entirely floating point. So advantages with such measures is that they are easy to understand, measure, and project, but there are fallacies. They may not be actually reflecting the performance. So once again, tutorial will take exercises which bring out the problem with these. So to summarize what we have learned, that you need good benchmarks, standardized benchmarks, which are available across the industry for evaluation and performance, such as spec. Measures like MIPS and megaflops look easy and simple, but they could be misleading. And one has to keep in mind Amdahl's law while talking of speed up due to some enhancements. So now, on the whole, in previous lecture and this lecture, we have seen that there are two measures of performance: execution time and throughput. We have focused on execution time, which is given by a simple formula. And these factors do get influenced by compiler technology, instruction set architecture, micro architecture, which means how instructions are implemented in hardware, and the basic circuit technology or fabrication technology. So when trying to improve performance, we should try to capture a large fraction, the common case, and try to make it as fast as possible. Okay, I'll stop with that.